Anyone? Can you guys hear me?
Yeah, I can hear you.
All right, good deal. Okay, so today is our last lecture. All right, and just remind you that our homework number 5 is due that exam day. So you still got some time. And if you don't know how to solve the homework, email me and we can schedule some meetings and maybe help you understand it better. And I'll try to schedule another review session next week, depending on the timing. And if not possible, I can also do a recording. And if you have any question about the content, please just email me and we can schedule another time to meet. All right. And then today we'll finish the column analysis and through an example. And perhaps I will go through some of the problem today from the exam. Okay, it's going to be quickly, but I think it's pretty straightforward. So I wouldn't worry too much about it. All right. So a quick review of what we have done from previous lecture. We have talked about the column analysis in terms of bending and axial force combined loading. All right. So in this combined loading condition, we said that the curve's going to go through A, B, C, D, E, 5 points, right? And depending on the strain condition, we have a called pure compression. And this case, that eccentricity is actually 0. There's no eccentricity, right? So the eccentricity is just 0. And then as we increase the eccentricity, the strain in the concrete column changes. And when there's no tension yet developed in the concrete section, we call it point of zero tension, right? And you keep going till you reach a point that the strain in the steel has reached the yielding strain. That is for grade 60, 0.0207. Then we say that, okay, it is yielded and you reach the balanced failure, right? And keep in mind that if I do a division line, I will say that before you exceed this balance failure moment, right? Balance failure. And you say that I can make a division line right here. And then this range right here between A and all the way between C, this is called compression controlled, right? So phi equal to 0.65, and this is compression controlled. All right, so this is very important. That is, after you do an analysis, that is, you get the PN and MN, you need to do the phi PN, phi MN, and E is dependent on the strain state, right? So for this state, it is between A and C, you have it, and that is called compression control. So phi equal to 0.65, phi equal to 0.65. All right, and now after C, you reach the balance failure, right? Reach the balance failure, meaning the steel has yielded, So now, if all the way that, let me use a different color. We divide that in terms of another division line here, say that before you reach the tension control limit, this stage right here, this is called the transition zone. Remember from the beam analysis, this is transition zone, right? So how do you get the phi from the transition zone? You use the equation, right? You use the equation depending on the strain in the steel, okay, which we'll talk about it. And then after that, last one, but not least, after your state exceed the tension control limit, that is epsilon s equal to 0.05, this is phi equal to 0.9, and this is tension controlled. All right. So now you see that once you figure out the P and MN, right, throughout the process, you will use the corresponding phi to find your design moment. Okay, so we talk about this, right? So we say that, okay, as our eccentricity changes, the stress state in the column changes, and correspondingly, the moment and axial loading changes as well. Right? And we say that, let's open it up and take a look at it, right? So we have now a compression force from concrete, compression force from the steel, tension force from steel, and then you can use these equations. And now notice that they do not balance equal to 0 anymore because they have axial loading, and they also have a moment. So your total moment, this is called internal moment, should equal to the external moment, right? So correspondingly, this is called the internal axial load on the left, and that equal to the external axial load on the right, okay? All right, so that, ladies and gentlemen, are the way to find out the axial forces and the compression inside. column right here, okay? Column right here. All right, so how to do that? How to do that? So let's start working on it. Before we go into example, one tiny detail I want to mention is that when you're trying to calculate the compression, right? It's this equation right here. So one, let's say Pn equal to a Cc plus Cs minus Ts, and that is the concrete compression equal to 0.85 F prime C A B, right? You know that from the beam. And then the compression from the steel equal to what? Compression from the steel equal to what? AS prime, FS prime. But as we studied from the doubly reinforced beam, there's a 0.85 F prime C inside this bracket. Why? Because you had to take the reinforcement out, right? And fill them back in. So that's what's the difference here. And now, so if this is concrete and this is the compression from the steel, and you also have a tension force from the steel, and that is ASFS. This equation here, ASFS, AS is the area of tensile reinforcement, right? You know that. Not too bad. But Fs is actually the stress state inside the reinforcement, right? How do you determine that? Turns out that you need to use the strain diagram to determine the epsilon Cu and then epsilon S, and then you use Fs equal to Young's modulus of steel multiplied by the strain to get the stress inside the reinforcement, Okay, all right, so that's the detail about the axial direction. In terms of bending moment, Mn should equal to the external one, right? Note that before you do anything, write down Mn equal to Pn multiplied by eccentricity E, and that equal to 0.85 F prime C A B. That is the concrete compression force, right? Multiply the lever arm. So here, how we take the lever arm is a little bit interesting. So instead of taking the lever arm as a random position, we say that we're going to sum the moment with respect to the centroid of the section. That means if this is the centroid of the section, then that is half h. When we're trying to find out the coupled moment, we're trying to find the distance for the coupled moment, we take the distance between the center of the total force to that neutral axis. So here it's going to be half h minus half a. All right, then this is for the concrete moment, and plus for the compression from the steel, that is AS prime, bracket inside FS prime, minus 0.85 F prime C. Okay, this is the compression force from the steel multiplied by the distance, which is half h, again, minus ds prime. Where is this ds prime? Ds prime simply is the compressive reinforcement distance right here, compressive reinforcement cover right here. Okay, all right, so that is half h minus ds prime. Now, last but not least, you have the tension from the reinforcement, which is ASFS, right? So that is ASFS, and the distance is ds minus half h. What is ds? ds is simply the depth of the tension side of the reinforcement. Okay, all right, so that is how we find out the moment capacity for the column. So with so many details in the equation, we can start working on the example now, right? So example, to solve or analyze a problem with a column, right? So given the column section below, okay, and we are going to determine several things, and soon you realize that these are basically the points along this envelope, along this axial envelope, okay? And now first is axial force Pn and bending moment Mn corresponding to the balance failure, balanced failure, right? So what is balance failure? Basically point C here on the envelope or interaction diagram. Okay, interaction diagram. So let me just say this is a P and this is M, and this kind of smooths over a belly button and come back, and this is called interaction diagram. Okay, interaction diagram. You mean, Bob, what are you talking about? What interaction? I'm looking at axial force interacting with bending moment. So this is interaction diagram, axial loading and bending moment interaction diagram. All right, so determine that. And of course, given that at prime C, concrete is 4 KSI, yield strength of bar 60 KSI, and we're going to determine the axial loading, right? And the bending moment corresponding point C. And the second point, we're going to ask you to determine Pn, Mn along tension failure region, along tension failure region. So this is a little bit tricky, right? I haven't heard this word before, tension failure region. What do you mean by tension failure region? That means if you have the compression failure region, which is right here, this is A, by the way, and B right here, C is right here, right on the bottom, B is here, E is at the crossing of the moment, right? So you divide that and you know that here, this is compression, and this is O tension. This is O tension. Okay, so that means I need to find a point between C, D, and E, C, D, and E, okay? So let me just label here. So this is trying to find the points between C and E, between C and E. And then number three, all we need to find out is, and again, Pn and Mn, nominal strengths for a point, excuse me, for a point in the compression region, in the compressive region. So that means I need to find a point from A to C. Okay, from A to C. And last but not least, I need to find a Pn and Mn for pure axial loading. Well, that is easy, right? For a pure axial loading point. Okay, so this means I'm going to find point A. Okay, all right. So apparently we're trying to find all these points, right? That is A, B, C, D, right? All these points, and then we can get this envelope or interaction diagram. So to solve this problem, right? Say solve, and starting from the first one, say trying to find out point C here, which is a balanced failure, right? Starting from the strain diagram always, okay? So this is balanced failure, and I'm going to start from the strain diagram. So strain diagram reads like this. I have epsilon Cu as a compressive strain of 0.003. I have a tensile strain of the steel that is balanced failure, right? Balanced failure meaning that is yielded. And again, it's grade 60, so the yield strength of the bar 0.00207, right? So that is the yield strength. And keep in mind that I do have compressive reinforcement, epsilon S prime. So how do you know that? I haven't given you the geometry yet, right? So the geometry is actually look like this: a square column, right? A square column, and I have a reinforcement in the middle. So this is number 9, corner, number 9, corner, number 9, corner, number 9, corner. Okay. And give you some dimensions, ds prime equal to a 2.5 inch. You say, wait a minute, Bob, how do you know this is prime? It's symmetric, right? So if I have another bars at the bottom, why you say the top bar is in compression? Because I assume that it is bending along the x-axis and assume it's a positive bending moment. Okay, assume it's a positive bending moment. All right, and by the way, x-axis in this case usually is called strong axis. In this case, it's square, so it probably doesn't make a whole lot of differences. But in the case of rectangular, the x-axis usually is a stronger axis. Okay, and the y-axis usually referred to a weak axis. Okay, weak axis. All right, now I know this is 4 number 9 bars, and I also have a stirrups. Tie them together. Look just like that. Okay, now given that it's symmetric, so I have a concrete cover C here equal to 2.5 inch. So the depth here is 20 minus 2.5, so 17.5 inch. And the total height, of course, for the section is given 20 inches. Okay, these are some geometries. All right, so now I forgot one thing. The width of the column, since it's square, is also so it's 12 inches. So it's actually not square, huh? So it's not square. So of course, if it's not square, this is shorter and it's longer this way. So x-axis is actually strong axis. Apologize, okay? X-axis is strong axis. Okay, all right, so now that's my geometry. So compared to the geometry and have my strain diagram, I need to know that not only I have tensile reinforcement, also I have compressive reinforcement. So I need to check the strain in the compressive reinforcement, right? Don't forget about that. Don't forget about that. So now corresponding geometry here, I know that I have a depth of the section that is 17.5 inch of D, call it DS, fine. And then I have the height of the total section that is 20 inches. Height of the total section is 20 inches, fine. And also I need to find out the compressive zone. I need to find out the compressive zone C. I don't know what it is, but I need to find it out. Okay, so from this geometry, simple geometry, I start from doing, okay, DS is 17.5. So compressive zone C should equal to the triangle, right? So epsilon CU, you should have seen this before in the beam analysis, right? Divided by epsilon CU plus epsilon S and multiply DS. Now bring the number in, so C equal to a 0.003, divide a 0.003 plus a 0.00207, and the whole thing multiplied by 17.5 inch, and that gives you a compressive zone of 10.3 inch. 10.3 inch. All right. So once you have this actual compressive zone, I need to find my effective compressive zone, which is A. So A equal to beta 1, C. You got it. So we need to have beta 1. Now, knowing that the concrete is 4 KSI, regular concrete, so beta 1 is 0.85, and multiply C, that is 10.3 inch. So A is actually 8.76 inch. A is 8.76 inch. All right. And now with all this, right, I can start mapping the stress in the steel. So the stress in the tensile reinforcement Fs, stress in the tensile reinforcement Fs, because it is balance failure, I know has yielded, so that equal to the yield strength of the bar, which is 60 KSI. All right. Now talking about the steel, I have my compressive reinforcement as well. Fs prime should equal to Es multiply epsilon S prime, epsilon S prime, and that should equal to Young's modulus Es multiply the strain in the compressive reinforcement, which can be calculated using C minus ds prime divided by C and multiply epsilon Cu. So bring the number in epsilon, bring the number in Es is 29,000 KSI of Young's modulus for steel and multiply by C, which we just obtained, 10.3 inch, minus 2.5 inch of ds prime divided by 10.3 inch again, multiply 0.003, and you got this number to be Fs prime to be at a 65.9 KSI. All right, 65.9 KSI. Now, when you see this number, your alarm system goes up, right? You panicked. Why? Why do I panic? Well, because you think of it, right? This number is what? This number is actually larger than the yield strength of the bar, which is 60 KSI, which is a big no-no. Is that right? We typically do not allow the bar to yield, right? In compression side of it. But since this is a column, ACI said, that's fine. If your Fs prime bigger than Fy, if this Fs prime bigger than Fy, and then we can use Fy instead. So we kept it at 60 KSI for column compression, okay? This is a little bit exception, okay? Kept it at 60 KSI, do not go above that, all right? Do not go above that, all right? So now I have the stress in tension. I say, look, the stress in the tensile reinforcement, it is 60 KSI. So now CC, the total compression from the concrete CC, got to equal to 0.85 F prime C A B, 0.85 F prime C A B, and that is 0.85 multiply 4 KSI multiply 8.76 inch. Where is this 8.76 inch? That is my A, which calculated previously. All right, multiply by the width of the column, 12 inch, and have this number down to be 357 kips, a total compression force from the concrete, 357 kips. All right, then the rest compression come from the steel should equal to AS prime multiply bracket inside Fs prime minus 0.85 F prime C. So number AS prime, how much reinforcement in compression? That is 2 inch squared. What is the stress in compression? We just calculated, that is 60 KSI capped, and then minus 0.85 of the coefficient multiplied the concrete, which is 4 KSI, and now you have it. So CS prime equal to a total force of 113.2 kips, 113.2 kips. And that is the total compression force from the reinforcement compression. Now for the tension, TS will equal to AS Fs. Now knowing that it is a balanced failure, so Fs equal to Fy. Why? Because it has yielded, right? So 2 number 9, 2-inch square multiply 60 KSI of yield strength, and that produces 120 kips of total tension force, And now with all of the three, I can say now the axial loading PM should equal to CC plus CS prime minus TS, because TS in tension, CC and CS prime in compression. So 357 plus 113.2 minus 120, and then I got this number to be 350.2 kips. 350.2 kips. So that is the total axial load I'm going to have for the column. Total axial load I'm going to have for the column. All right. So apart from that, I want to find my bending moments. Excuse me. So bending moment Mn, use that equation, should equal to the compression force CC multiplied by the lever arm half H minus half A, and plus CS prime, compression force from the steel, half H minus DS prime, plus Y plus, because tension side, it is in the negative, but when you talk about the moment direction, it is the same direction. It is the same direction. In case you're still confused, take a look at the section, right? Take a look at the 3D view of the section, okay? And now I'm saying, look, this is x-axis. So the axial loading force is going to be compression here, CS prime, compression here, CC, and tension here, which is TS, right? When you're summing the moment, you're summing the moment with respect to the neutral axis, x-axis here, right? So you have a moment of CS prime going, if I look at from the right-hand side rule, meaning looking from the left side, right? This is a counterclockwise, and this is CS cause the moment, CS prime, and then have another moment, CC, and also I have another moment positive in the same direction, TS, right? So they're in the same direction. Therefore, it is not a minus sign, but a positive sign here, and plus a TS multiplied by the distance, which is DS minus half H. Okay, all right, so since this is positive, I just have to bring the number in here. Now inside this number, 357 kips multiplied by the distance, which is 10 inches of half height, minus 4.38, which is half of A, plus CS prime, 113.2 kips, multiplied by a half H, 10 inches, minus 2.5 inches of a concrete cover, plus 120 kips of force, multiplied by a DS 17.5 inch minus half H, 10 inches. And now I got the whole thing divided by a 12-inch per foot, convert everything into kip foot. So I have this whole number to be 310 kip foot. Okay, 310 kip foot. So now I have my PN, which is axial loading here. Where is my PN? Where is it? Okay, PN right here, and Mn, which is the bending moment. So I want to find eccentricity because I can do that, right? Now E equal to Mn over Pn, right? And that equal to a 310 kip foot and divided by a 350.2 kip. So I get about some here in terms of foot, about less than a foot, and then convert back to inches, 12 inch per foot, and then that is 10.66 inches. Okay, 10.6 inches. And just to remind you where it is at on the interaction diagram. So this is my interaction diagram, P and M, and I know that my curve looks like a nice belly button. Go back here. So C actually right here. Okay, and point C here has an axial loading of 350, let me see if I read it, 350.2 kip, and have a bending moment of 310 kip foot. Okay, so this is Mn and this is Pn. All right, so that's where the point C is at. That's where the point C is at. Now, if you really want to put a number on it, because I have my eccentricity, you say eccentricity at this point is equal to 10.66 inches. So what is this 10.66 inches? That means if you go back to the cross-section view of the column, cross-section view of the column, okay? I'm drawing the column here, and this is my x-axis. So 10.66 means that away from the neutral axis, 10.66 inches. And now the height of the column is 20, so half of it, 10 inches. 10.66 meaning I have to put my force 0.66 inch outside of the section, which means the axial force loading is along this y-axis, but right here, 0.66 inch away from the edge of it, from the edge of it. So that means this eccentricity is right here, and it is 10.66 inches. Okay. All right. So that's for point C. That's for point C. So how about for point others, right? Other points, point D and E, and also everything, right? Now, second point, excuse me. We were asking to find a point in tensile zone, in the tension zone, right? Tension region. Means anywhere between C and E would work. Anywhere between C and E will work. But let's just say that I'm interested, find a point between D and E, between D and E. What is D? D is the tension control limit, all right? So just to make sure that D, we know that is tension control limit. So tension control, strain of steel, 0.005. You say, Bob, wouldn't you want to use epsilon T? But here I only have what? One layer of reinforcement, right here, right? So that means my epsilon S equal to epsilon T, and that is 0.005. All right. Now, as I said, I'm going to find a point that between D and E, knowing that I'm getting a little bit more tensile strain as I'm approaching the point E. So I'm going to find a point at strain of 0.007. This is just assumed. Okay. Anyway, this is larger than 0.05, right? Larger than the point D. So making that assumption gives me a nice strain diagram, right? So my strain diagram looks like this right now. So on the right-hand side, I'm going to draw my strain diagram. So epsilon Cu steel equal to 0.003, and strain the steel right here, epsilon S equal to a 0.0075. All right, not inches, bad habit. Okay, and I am going to find out the compressive zone C, and on top of that, I'm going to find out epsilon S prime, which is the compressive strain. All right, so start thinking about it, right? Start thinking about it. First thing coming into your mind that because it is in a tension control zone and is over the tension control limit, so naturally the tensile stress in the bar has to equal to the yield stress because everything yielded, right? So at this point, I can start doing my compressive zone size C, and that is equal to ds multiplied by the epsilon Cu on the top and divided by epsilon Cu plus epsilon S, and ds equal to a 17.5 inch, epsilon Cu 0.003, and bottom here at 0.003 plus assume the number of 0.0075. You say, Bob, why go with 0.0075? Can I go to 0.01, sorry, 0.09 or 0.01? Sure you can. Any number would work. I'm just picking a number that's larger than 0.005 to satisfy the requirement, okay? But nevertheless, after everything said and done, the actual compressive zone size C equal to 5 inch, and effective compressive zone size A equal to beta 1 C, and that is 0.85 multiplied by 5 inch, and I got this number to be a 4.25 inch, 4.25 inch. All right, so quickly I get my strain in a compression epsilon S prime equal to a C minus ds prime divided by C and multiply epsilon Cu, and that is 5 inch minus 2.5 divided by 5 and multiply 0.003 and have this number to be a what? To be a what? Well, let's take a look at it, right? This is basically 1/2 of 0.0015. Is that right? 0.015. Okay, so 0.015, what does it mean? What does it mean? It means that this is less than yield strain, okay? This is less than the yield strain, so okay. Okay, hasn't yielded yet, which is a good thing, okay? And I'll know that for sure because now if I do the stress check, Fs prime that equal to Es epsilon S prime, and that gives you a 29,000 KSI of Young's modulus multiplied by the 0.0015. and you're left with a 43.5 KSI, which is much smaller than the yield strength of steel, which is 60 KSI. So your steel hasn't yielded in the compression side of it, Okay. All right. Like I said, this is pretty dry so far, right? So you're just going to carry on, find out the compression size from the concrete, and the CC equal to 0.85 F prime C AB, no surprise, using the equation. So 0.85, plug the number 4 KSI, and A equal to a 4.25 inch, and B 12 inch. So I got this number to be 173 kips. Okay. And then CS prime, which equal to AS prime, and bracket inside FS prime minus 0.85 F prime C, and bring the number AS prime 2 inch squared, and FS prime 43.5 KSI minus 0.85 F prime C 4 KSI. All right, and then this whole thing equal to a 80.2 kips. Okay. So all of from the compression, I got around, say, 80 plus 172, 253 kips. So the tension force TS equal to ASFY, and this equal to 2 inch squared and multiply 60 KSI. I have a total tension force of 120 kips. And note that this is not the AA reinforced section. So you don't have to balance everything. You don't have to balance anything, right? And there's no need for iteration, right? You go in straight and find out the axial force Pn would equal to CC plus ES prime minus TS, right? So that is 173 plus 80 minus 120, end up 133 kips of total axial loading. All right, now Mn, which is the bending moment, I can save you the hassle, just write out the number. So this is that for the compression, CS prime part, which is this. I'm repeating the equation again. You should find it from step 1, but that's fine. TS and the ds minus half h. And all you have to do, bring the number here, 170 multiply 10 minus 4.25 divided by 2 plus CS prime, which is 80, and multiplies 10 minus 2.5 and plus tension force 120. Again, this is plus sign, okay, folks? Minus in the Pn, plus in the Mn, okay? And then 17.5 minus 10, okay? And the whole thing bracket together divided by a 12 inch per foot, convert back to foot. And I have now a 238 kip foot. All right. So as always, your E eccentricity would equal to Mn over Pn, and that is equal to 238 divided by 133 and multiply 12 inch per foot, convert back to inches, and now you have 21.5 inch of eccentricity. To put it here, 21.5, meaning you have a actually higher eccentricity than point C here. So your distance between the axial force P here and the centroid, which is x-axis right here. So this is E eccentricity is equal to 21.5 inch, 21.5 inch. All right, so there you have it, right? There you have it. So where it is anyway, so now you put the interaction diagram on the right, you put the interaction diagram on the right. Sometimes I write Pn, sometimes I write P, they're the same thing, okay? Sorry about that. So now here is A, and I don't know A yet, but I know it's somewhere. And I have B, which is a zero tension. I don't know where it is yet, but I know C, which I just calculated out from previously, right? And then go along, I have D somewhere here. And now I have E, and this point we're calculating is right here. This point we're calculating is right here, and label it up, right? This one here has a 23.8 kip foot of moment, Mn, and then axial loading of 133 kip Pn, and then eventually have eccentricity E of 21.5 inch. So these three numbers describe this point, All right, so there you have another point. Then you keep marching on, right? Next point is find a point that between A and B. So number 3, find a point between A and B, Okay, like I said, today is pretty dry, okay? It's just a lot of calculations, right? So between A and B, I'm trying to find a point here. I don't know exactly where it is, right? So let me just label 3. And if this is number 1 and this is number 2, so So this is number 3, right? So I know it's going to be between A and B, right? So all I have to do is find out what condition describes this point. Describe this point. So first, let's take a look at the strain diagram for A. And A is pure axial loading, so the whole section looks like rectangular, and the strain reads like this, right? Strain reads like this. Now, one thing for sure, the compressive zone is much larger than the depth of the section. It's infinite, right? It keep going, it's parallel, right? It's just keep going into compressive zone, right? Now, this is point A, and point B, I have a zero tension. Remember, zero tension, meaning this entire strain distribution looks like this. And now it's a zero tension, meaning the whole thing looks like just like that. So C, compressive zone, is still bigger than or approximately equal to ds. Approximately equal to ds. So that means that I need a point somewhere in between, and this point is 3 here in between, right? In between. That means I need to find a depth, need to find a compressive zone much larger than the depth, okay? So how to pick this number? I know ds equal to 17.5 inch. So I'm just gonna say, look, I'm going to pick a number that C equal to 18 inches. C equal to 18 inches. All right, now with C equal to 18 inches, right? So pretty much I have my strain diagram set. Compressive zone C equal to 18 inches. Okay, I may have a little bit tension zone. but I may have a little bit tension zone, but I may not have a tension zone, right? So think of it. This case, B here, my compressive zone equal to the ds. So if I go further, I will have tension. Between A and B, I would not have tension, right? So C equal to 18 inch, C equal to 18 inch. That means that I have a full compression still. And knowing that, I can draw this and I say that, look, it's going to go along here, somewhere here, and this is 18, and then somewhere have my 17.5, which is ds, right? ds is right here, 17.5 inches. And why I'm putting the ds out, because this will be epsilon s tensile strain, and I know that tensile strain is in compression as well. Be careful, okay? Tensile strain might be in the compression as well, all right? But before we do that, right, let's go back to take a look at the real compressive strain in the steel on the top. Now this is epsilon s prime, and ds prime here equal to 2.5 inch, okay? So now carry on, right? So with all these assumptions, I'm assuming that the compressor is 18 inches. So from there, I say C equal to 18, so A equal to C divided by beta 1, and that is 18 divided by, A equal to beta 1 C, beta 1 C, so 0.85 multiplied by 18 inches, so A equal to a 15.3 inches. And that is my effective compressive zone. So given this effective compressive zone CC, which is a concrete compression force equal to 0.85, and multiply 4 KSI of concrete, multiply 15.3 inch of A, this is A, and then width of the section 12 inch. And I got this number to be 624 kips, okay? Now, I'm not going to bother you with the details. So I'm just going to write quickly out Fs prime equal to Es multiply epsilon prime and equal to 29,000 KSI and multiply by a strain in a compression. So I know that C minus ds prime divided by C and multiply epsilon Cu. So bring this number to multiply C, which is actually, sorry, one student here, 10 inches. C is 18 inches, right? 18 inches minus 2.5 divided by another 18 inches, and then 0.03, okay? Okay, and then this number turned out to be 75 KSI. Should I be happy about it? No, I'm not. Why? This is much larger than the 60 KSI of yield strain. So per ACI, I say let Fs prime equal to a 60 KSI and be done with. Okay, capped it at 60 KSI. Okay. All right. So now with this, we can go on to find out other things, right? So the tensile stress, right? Tensile stress Fs equal to ES epsilon S, and that equal to 29,000 KSI multiplied by the strain and the tension, right? Strain and tension ds minus C divided by C multiply epsilon CU. So bring the number in 29,000 KSI multiplied by 17.5 minus 18 divided by 18 and multiply epsilon CU 0.003. Okay, and then I find out this stress to be a surprising negative 2 KSI. Oops, what do you mean by negative KSI, negative 2 KSI? Well, the tensile stress for the steel is supposed to be positive, Well, you actually find out it's negative. That means that it coincides with what we said before. The stress in the tensile reinforcement in this case is actually compression. It's actually compression because there's negative sign in front of it. All right. So the tension force, quote unquote, the tension force using quotation mark, okay, it's not real tension anymore, but let's say this tension force still equal to AS FS 2-inch square of steel multiplied by a negative 2 KSI. So that is negative 4 kips. It's actually in compression. How do we reflect that? Well, we reflect that through Pn equal to CC plus CS prime minus TS. So 624 kips of CS plus 60 KSI multiplied by 2-inch squared. That's total compression force I have from steel minus another minus because there's a sign in front of it. So minus minus plus. And now I have the total compression force of 748 kips. All right. All right. So this just shows you that the tensile reinforcement does not always bear tension. Sometimes they bear compression as well in the column. All right. So Mn, now there are long equations. So save me the trouble, save you the hustle. I'm just going to write out the numbers, okay, to equal to 624 multiply 10 inches minus 15.3 inches divided by 2. And if you care to know, 15.3 is actually A, plus 120 kips multiply the distance, which is 10 inches minus 2.5 inches of ds prime, and plus ts prime, and no, not prime, okay, and plus, okay, and now ds, which is here, ts right here, just here, minus 4 kips, okay, minus 4 kips, okay, there's a in front of it, yep.
Why is CS prime 60 times 2?
Because there are 2-inch squared, and we say fs prime equal to that. So
we don't need to subtract the 0.85.
Oh, you're right. I forgot about that. Did I? You're right. Absolutely. Sorry. Yeah, I think I made a boo-boo here. Okay. All right. You guys have to help me out here. I think I made a boo-boo last night. Okay. Let me make this clear. So 6224 plus CS prime, which is, let me see this, AS prime, bracket inside FS prime minus 0.85 F prime C. Is that right?
Yeah.
So this AS prime 2-inch squared. Let me do this. FS prime is 160 KSI minus 0.85 for KSI. Natalie, can you crunch this number out real quick for me?
Yeah.
I made a mistake here. Apologize.
It's 113.2.
113.2. This is the kips, right? Okay.
Yeah.
Can we confirm this number? Apologize, I must made this mistake last night. Forgot this minus 0.85 prime C. 113.2 kips. Do we get a confirmation? Any one of the folks here?
That was the same numbers earlier.
Same number?
Should be good.
Okay, good. All right, good deal. Now, apologize, let me make this up. So this is minus, and this is plus 4 kips. Okay, now I lost this number, so I may have to ask you guys help me out here. 624 plus 113.2 plus 4, what you guys got?
741.
741, okay, her 2 voices, great. Okay, 741, let me compare to what I have here. Okay, I lost a few. Yeah, all right, that makes sense. 741, okay. Yeah, thank you, Natalie. That's a correction, okay, apologize. must have fallen asleep last night. Anyway, so that is that. Now, let me be careful here. 624 kips in terms of moment. This is 10 inches minus 15.3 inches divided by 2. And this is plus 120 multiplied by, now this is not 120 anymore. So this is 113.2 multiplied by 10 inches minus 2.5 inches, right? And then this is minus 4 kips multiplied 17.5 inches minus 10 inches. All right, folks, since I lost that number, you might have to help me out here. Mn equal to this number right here. Can you guys help me quickly crunch it out? And this has to divide by 12 inch per foot, okay? Okay, I'll wait for you to crunch this number, but my number, my round number is 190 something. I hope I just have a round last digit. Okay, so quickly help me crunch this number out and let's see what you get, okay? 124 multiply 10 minus this, 113.
Got 190.5.
Okay, do I get a second?
Yeah, I got that too.
You got that too, okay, thank you. So sorry, okay. I forgot the minus 0.85 things myself. Okay, this is very important. Let me just mark this. Okay, so this is close. I got 195 previously, so this is close. All right, okay, so with that, I think my numbers stay correct. So E is Mn divided by Pn, and Mn equals 190 kip foot divided by P741 kip. So I can probably do this myself while you guys help me check on that. Let me see what I get. 190 divided by 741. So this is multiplied by 12 inch per foot. And I got a, do this 12, 3.07, 3.08. Anyone? You guys get same? 3.
Yeah.
Okay, good. Thank you. So this is 3.08, right? So what it means by that is I draw my section out and my axial loading is within the section, but this is x-axis, okay? And it's within the section, and this is E equal to 3.08 inch. All right, okay, so now thank you for the correction, guys. And we now have the corrected interaction diagram, Pn and Mn. Very happy actually for you guys to help me here, showing you guys pay attention. And this is belly button, nice. And A is right here, B is right here. And what we just did is 0.3 somewhere here. And then C is right here, which is also 0.2 or 0.1. And again, we didn't do D. We didn't do E, but we did another point right here between D and E right here. Okay. And now just to label this number 3 here, and this number is 190.5 kip foot, which is the moment. Axial loading is 141 kip, and eccentricity is 3.08 inch on the curve. Okay. All right. So last but not least, right? So we have now number four, and that is my pure compression, the pure axial load. Okay, pure axial load. I think this is pretty straightforward, which is A, okay? And now think about the strain diagram, right? It has nothing but its rectangular strain distribution, and all of them is the same. Horrible drawing, apologize. Let me clean this up real quick. Here we go. Okay, so this is my strain distribution, and I know, now guys, this is a bit different, okay? From previous lecture, this axial loading equal to P naught equal to 0.85 F prime C, bracket inside is a G gross section minus AST, the reinforcement area, plus FY and AST, plus FY AST, okay? And now I can bring the number in, so Pn equal to 0.85 and 4 KSI, and then multiply AG gross section 12 inch, multiply 20 inch minus 4 inch square of number 9 bars, plus a 60 KSI, and then 4 inch square of steel. And then I have a total of axial load of very large number, 1,042 kips. And I know that since it's pure axial loading, there's no moment, there's no eccentricity. So drawing this on the interaction diagram, Pn, Mn, and my nice blue button right here, okay, and these point A, which is also point 4 here, and B, oh, B hasn't calculated that. I haven't calculated B here, but let me just finish this. So B is somewhere here, and D is somewhere here, E is someone here. So A, number 4 is here, number 3 is right here, and number 1 is right here, which is C, and number 2 is right here. So now, if you were given 1, 2, 3, 4, you can still try to complete this moment, axial loading moment interaction diagram. All right, but now if we were asking you guys to find out the phi, say, okay, how about phi for 1, 2, 3, 4 points? How are you going to do that, right? So now, knowing that if you draw a line between 0 and C, this region here is compression control, so phi equal to 0.65. And this region here between C and D, sorry, my phone call. So here is phi equal to a transition zone. Okay. And then here, phi equal to 0.9. All right. So apart from 1, 2, 3, 4, all these points, right? 1, 2, 3, 4, all these points, right? Now 0.1, phi equal to right here. Okay. Phi equal to right here. So what is 0.1? It's 0.65. It's on the balance point, but still, right? 0.65. 2, where is that 2? 2 here is 0.9, phi equal to 0.9. 3, phi equal to 0.65. 4, where's the 4a? That is phi equal to 0.65. Okay, and that's how you get phi, and then multiply by the phi in front of Pn and Mn, you will get all these numbers. You will get all these numbers. Okay. All right. So you can see that it's quite a tedious process. Quite a tedious process, right? And actually, to make it easier for us, we didn't ask you straight to find out A and B and C and D and E. We asked you to find some points along the line. But in the exam, we typically ask you guys to find A and B and C and D and E. You say, Bob, how do I find A and B and C and D and E? You didn't do exactly that in the example. Well, let's take a look. We did A, exactly, right? Pure axial load. Now we did 3, we didn't do B, but the difference is that for 3, we say C equal to 18 inch. C equal to 18. For B, C just equal to the entire DS, right? Entire DS, and that is 17.5 inch. Okay, now for C.1, we did that already. You know how to do that. We didn't do D, we didn't do E. For D, it's actually epsilon S equal to 0.005 instead of 0.075 we assumed in the example, right? And now for E, how do you get E? Well, if you're going to get E, first thing you know that it has no axial loading, Pn equal to 0, right? So that means you just treat your section as a AA reinforced beam, AA reinforced beam. So it's a turn a column into a beam and you just do a beam analysis. Okay, all right. Okay, so now we're done. We're done. Everything in the course has been completed. All right, and now I think we're ready to take on the exam. I will probably talk about the exam a little bit before I go on. Any questions about this boring stuff? It's tedious stuff, a lot of stuff. I know. Any questions about it except the error we made, but corrected thanks to Natalie? Anything? Anything? Okay, if nothing else, I'm going to talk about the exam a little bit, just a little bit. All right, and then sit tight. We'll show you some problem. Okay, show you some problem. And now one thing is that for the homeworks, number 6 is not going to be collected. Okay, it's not going to be collected. You can follow the example and we can talk about it. But now let's get back to the exam, all right? Get back to the final exam. And this is the exam I posted. This is the exam I posted. So give me 1 second. Let me see here. Final exam, final exam. All right, so let me share screen with you guys. You guys can see this. All right, do you guys see my screen? You guys see my screen? Can you guys see it?
Yeah.
Yes. Good deal. Okay, so problem number 3 is a column, right? So this is actually a bending about 1, 1 axis. In the example, I call it XX, but in the here, I call it 1, 1, but it's the same thing, okay? It's the shorter side, right? And material property of prime C, 4.5 1000 PSI, 4.5, okay, 4,500, right? The beta 1 is not 0.85. Let me say this again. A lot of students make this mistake, okay? Beta 1 is not 0.85, okay? Because this is 4,500 PSI, okay? Fy 75,000 PSI, 75 KSI. Be careful, okay? I'm tricking you, right? Why? This changes a lot. This changes a lot. What does it change? It changes yield strength. It's not grade 60 anymore. It's grade 75. So yield strength changes, okay? And also when you're trying to do the comparison between the compressive stress of the steel and the yield strength, you use this to cap it. You use 75 KSI to cap it. No longer 60 KSI. All right, okay. Now, before you do everything, look at the cross sections for number 10. For number 10 is not for number 9, for number 10, okay? For number 10, all right? So need to know what is the diameter or an area, cross-section area of the number 10 bars, okay? If you forgot, go back to table 5, back in the textbook, okay? All right, 2.5, a concrete cover, so symmetric 2.5 at the bottom here, 12 inches width, 20 inches, pretty much just like the homework, sorry, just like the example we just covered, okay? Now, determine blah, 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 and find out these point 1 corresponding pure axial compression load. This is actually point A. This is point A, okay? Corresponding to balance failure, point C, okay? Now, careful, corresponding to epsilon S equal to 4.4 times epsilon Y. So tell you the strain in the reinforcement. So you have to draw the diagram, okay? That means these two bars will see a 0.00 something, right? It's no longer 0.207, okay? 75 KSI, okay? Multiply 4 times. So need to find out Pn, Mn, you can do that, right? Once you find Pn, Mn, you need to find phi to get phi, Pn, phi, Mn. It's pretty straightforward, right? Where is the phi coming from, right? Take a look. Now, we said point 1 is pure compression, right? So that is point A, so phi equal to 0.65. Point 2 is C, balance failure. It just getting into the tensile failure regime, right? So phi equal to 0.65 again. Point 3 corresponding to epsilon S equal to 4 times epsilon Y, 4 times, okay? 4 times. It must exceed the tension control limit. It must exceed tension control limit. Don't believe me? Try it out, okay? Try it out. What is tension control limit? 0.005. What is epsilon Y for 75 KSI? Larger than 0.027. So 4 times that is larger than 0.008. Must be larger than 0.05, which must be tension control. So phi 4.3 has to equal to 0.9. Okay. All right. So determine maximum value phi Pn, term Pn max interaction diagram on the next page. Okay. So you just have to draw the diagram and find out, right? Draw the diagram, find out. Now, is the column adequate to support a factor as you're loading 400 kips, a moment about 1 axis mu, 200 kip fit, justify answer using interaction diagram? Okay, this is wonderful, right? Now, how to do this? Suppose like you find A here, I'm making things up, I don't know, okay? I'm making things up. A here, which is 0.1. B, let me clean this up and do this first. Shrink it down a little bit, all right, there you go. And this is A somewhere here, okay? I don't know the number, okay? I'm just making things up. Suppose you find A right here, and C, right, is right here. I don't know, again, I'm making things up, okay? 3 somewhere here must be very close to E already, right? Definitely, E is right here, but definitely way past D, okay? But this is, so this is 3, and this is somewhere, say, called 0.3. This is actually 0.1. This is actually 0.2, right? So you know your moment diagram. I say, just say this is my moment diagram. Okay. Oh, sorry, it has to pass through. Okay, it has to pass through. Okay. But anyway, this is my assumed moment diagram, right? Before I do phi, this is assumed moment diagram before I do phi. Okay. Now, once you do phi, you scale this back down to 0.65. Remember? Okay, up to C here. You do a line here. My line is horrible, but let me try to erase this. because, okay, because folks, you have 0.65 of phi in this compression controlled region. So you scale down by multiplying phi equal to 0.65. All right, and you also scale down because there's a transition zone. So connected to the D point, you transition from somewhere here to somewhere here, okay? And then 0.9 somewhere here. So this phi factored envelope, which is inside this outside envelope, is your actual design envelope. Let me say this again, okay? You probably haven't realized that. Outside envelope is Pn Mn. After you multiply phi in front of both of them, you scale back down to a phi Pn Mn. So meaning the design envelope phi Pn phi Mn is actually inside this Pn Mn. Let me say it 3 times, okay? So you won't forget. Outside the envelope, which is from your calculation, 1, 2, 3 points, connect them together to get you a belly button, to get you the envelope. You multiply in front of a phi to get your designed envelope, which is inside of this outside envelope. All right. Now, once you have this, it reads out to say that if PU is 400 kips, so PU given, let me just scroll up to show you, right? PU is 400 and MU is 200. So corresponding to my curve, PU is 400. Where's PU? PU 400 right here, somewhere, right? And MU is 200. So this is MU 200. So I have a point here. If this point, let me say this, if this point is inside the design envelope, which is inside phi Mn, phi Pn, then you're safe. Now, if this curve, this point is outside of phi Pn, phi Mn curve, then you're not safe. All right. I know this is confusing, so let me say it again so you will understand, okay? Now think of it, if your design envelope is phi Pn, phi Mn, then any applied loading considering Mu and Pu, if this design loading point is inside this envelope, you're fine, you're safe. But if this point is outside this envelope, then you're not safe. Is that right? So that's how are we going to do this problem. Okay. All right. Any questions about this? Any question about this? Anything? This is very, very important because you see almost exactly the same problem, okay? Besides that, the geometry will change, number will change, but the problem will not change, okay? This will be the column problem. So if you have any question about it, folks, if you're watching from home, any question about it, let me know, okay? Let me know, okay? All right, so that's about it. I'm gonna clean this up and say that this is the first column problem. All right, so let's take a look at another column problem. Now the difference between this column problem and another column problem is that I have a middle reinforcement, middle layer reinforcement. Now, supposedly, if you have another middle layer reinforcement, your calculation method does not change, but depending on where your neutral axis is at, you need to say if the stress in the middle layer is in compression or stress in the middle layer will be in tension. You have to judge by that. But let me help you out here. Since we only have one problem in the exam, you will not, and I promise you this time, you will not have middle layer reinforcement in the final exam, okay? I think in last year's exam, when I made it, I mentioned this to the class as well, but I ended the last hour, I forgot about it and got a lot of questions from the folks. So this time, let me make it very clear. You will not see a middle layer at all, okay, in this exam. You will not see a middle layer at all in this exam, okay, in this exam, all right? Okay, but other than that, this problem is almost identical from the previous one. Instead, 2 bars, I have 3 bars on the side, 3 bars on the side, and this is square, okay? This is square. All right, quite exhausting, eh? But that's it. So it's not too bad for a column problem. That's not too bad, all right? And I'm done. And one more thing, folks, help me out here. Please fill in the survey, okay? Please fill in the survey. If you have any grievance, any problem, I know this semester I've been on a medical leave, but still trying to make it whole. So I must have, hopefully I maintain the integrity of the class, but if you feel like something I missed, I need to improve, let me know, fill out the survey, okay, so I can improve. And thank you so much for a great semester. And I will release the time for the additional review. If not, it will be recorded, so you'll see it at home, okay? And if you still don't know where your final exam is gonna be, check on the calendar, okay? Search Missouri S&T final exam schedule, you should be able to see it. Okay, and I'll send an email reminder, of course. Thank you very much, and I hope to see you in the near future. All right, bye now, and welcome any questions.
Thank you, Bob.
Professor.
Yeah, no problem. Thank you.
Thank you.